Today's learning targets. I can successfully use the properties of continuous functions. Yes, there are properties, but you know what? They are very, very simple. I can algebraically determine problems using the intermediate value theorem for continuous functions. Okay, we're starting to get into what we call the heart of calculus, but as the next few lessons come, you'll see what I'm talking about. All right, so here we go. Properties of continuous functions. If the function f and g are both continuous at some random point x, if you have two continuous functions, f and g, then the following combinations are also continuous at that x value. Meaning, okay, f plus g. Let me give you an example. If I know a straight line is continuous, right? Let's say f of x equals x. That's like the line y equals x, correct?
Yeah.
It's a diagonal, that is continuous. Let's say g of x is x squared. Is it a parabola? That's continuous. There are no breaks in it, is there? Are there?
No.
So that means if I add f and g, that sum is also continuous. So I could take x plus x squared, and I get x squared plus x. This function is also continuous because the two functions that make it up were continuous. Okay? It's always easier when we explain it with things we know. I know. We know. I know. You know.
Oh.
Anyways. Thank you. Now, there's a difference property, which means I could have taken, thank you. That takes a second to get some of these jokes. I could take f of x and subtract g of x, and that would also be continuous. So I could take my x, and I can subtract my x squared. And this function would be continuous because the two individual functions that make up are continuous. So, we also have a product. We have a product property. F times g would also be continuous. Let's think about it. If f, okay, I keep on referring to this. If my f function is just x, and I multiply that times my g function, which is x squared, x cubed is also continuous. Isn't it just a line that goes up like this and like this on the axis? It's continuous. Just basic rules. Okay, constant multiple. Constant multiple. What does that mean? That means if I take any constant and put it in front of the function, that's continuous. That product will also be continuous. For example, someone give me a number.
3.
With 7, I heard 7 first. 12 was louder, but 7 came first. If I take 7 and multiply it, that's a bad 7. I take 7, and that didn't help. It looks like a cursive F. If I take 7 and multiply it times my function x, that's F, right? If x is continuous, well, 7x is continuous too. That's just a straight line, isn't it? Yeah, man. Yeah, man. For any number k. Interesting. What if k was 0? Would it negative 7 also be a straight line? Negative 7x? But what about if it's 0? What is 0 times x? It's just 0. So if I have an equation, y equals 0, isn't that a straight line?
Yeah.
Yeah. It's also, y equals 0 is a horizontal line, which is the x-axis. It goes through the 0 on the y. It's not undefined. I can have a 0 as a number. I can't have 0 on the bottom of a fraction. And I cannot have negative numbers on the radicals. Okay, and the last one is obviously the quotient rule. You can divide them, and that would be a continuous function. Okay? So if my f is the function x divided by g, which is x squared, that's also continuous because x and x squared is continuous. Now, there's one exception, and we just said it. My g function can't be 0. Yeah. because it's undefined. But this, you could have said y equals 0 is a continuous. It is, unless it's on the bottom of a fraction, because you can't have zeros on the bottom of a fraction. Come on. If f is continuous at c and g is continuous at f of c, then the composite g of f is also continuous at c. Basically, if you have two continuous functions, their composite is also continuous. Let me explain what composite is. Let's say f of x equals x plus 2. Okay? Let's say g of x is x squared. And these are both continuous. This is a straight line. It's a parabola. They're both continuous. Now, if I do the composite g of f, right? Or better yet, let's do it this way. Remember when I told you composites are when you take one function and put it in the other? If I take f of x and put it into g of x, that should also be continuous. Isn't g of x x squared? If I take this function and put that into my variable here, x plus 2 squared, that's a composite of the two functions. When I take one function and I put it into the other, if I do that, isn't that the same as saying g of x plus 2? Because that's what that is. That means wherever there's a variable here, I replace it with x plus 2, which is x squared plus 4x plus 4. This is also continuous because it is the composition of two continuous functions. Got it? Mm-hmm. Yes, right. Now, show that the following function is a continuous function. All right? Are you ready? I'm going to walk through this one. Now, I have this right here. Y equals, that's x sine of x all over x squared plus 2 inside the absolute values. Let's break this up as a composition of two functions. I can say one function, we'll call it f of x because we use f of x and g of x a lot. It's just the absolute value of x. Looking at this right here, this whole thing, what would g of x have to be? What is g of x inside f of x? What goes inside the absolute value bars?
Plus or minus?
This whole thing goes in the absolute value bars, doesn't it?
Yeah.
So that's like what would go inside here, isn't it? So I can say g of x, which goes inside there, is x sine of x all over x squared plus 2. Okay? So in order to show that this whole big function is continuous, I got to make sure the two functions that make it up are both continuous, right? Because if they're both continuous, then you do the composition of them. The composition is continuous. This is continuous. What is the graph of the absolute value? Notice it's a B. The graph looks like a B. Absolute value looks like a B. That's continuous. Hard to graph that. That would look like this. That's continuous. Okay? Bang. Continuous. I've got to make sure this is continuous. And we can use some of our properties. I can use division, right? So if x times sine of x is continuous, and x squared plus 2 is continuous, isn't that my division property? If you divide two continuous functions, that means the fraction or the quotient or whatever is continuous. Well, isn't this a parabola that's just moved up too? That's continuous. It's a parabola. What about x times the sine of x? I can graph it, but without even having to graph it, wait for it. Don't try. You don't know what that graph looks like, but wouldn't you know what the graph of x looks like? And what about the graph of sine of x? So I'll use my product rule. If both of these are continuous, then the product of them will be continuous, won't it? Isn't x just a straight line? That's continuous, bang. Isn't sine of x just, it goes like this forever? That's continuous, isn't it? So let's go backward to the original function, okay? And I want everybody to get caught up with me as I explain this. Don't even look at your papers, look up here when you're done writing, okay? Put your pencils down when you're done writing. Okay, now, we know x is a line that's continuous. We know sine of x is continuous. It's the sine function, the sine curve. That means their product is continuous, right?
Yes.
We know this is a parabola that's continuous, correct? So that means these two, when I divide them using the quotient property, that means this is continuous. Well, I know the absolute value of x is continuous because that's just a v. So if the absolute value of x is continuous and this whole quotient is continuous, then the composition of them is continuous. Thank you. I accept 10s and 20s. Get out of my class. Come on. Show that the following function is continuous. I want you guys to try and break this one down yourselves. I'll give you 5 minutes, and then we'll go over it. All right? All right. What's the first thing I'm going to do to prove that this is continuous? Great. Yes. Okay, I'll start by saying, okay, I can have radical x as one of my functions. You know what? Screw that. B. H is for the other function. You use your initials. Go nuts. What would my other function be? What goes into the radical here? Yes. The whole thing is what was substituted for this x, wouldn't it? So I have x over x plus 1. Now, I don't know if you can recognize what the graph of radical x looks like. Like you can recognize a parabola or a straight line. But actually, the graph of the square root function starts here at 0, so you can have 0 there, and it goes like this. Forever. Because for every value of x, you know, like if x is 4, y is 2. Square root of 4 is 2. It's smaller. For x is 9, y would be 3. So the further this goes this way, it goes up slowly, but this way fast. It goes to the right fast and goes up slowly. So that is continuous. Yes, but yeah, 1 second. But yes, I do. So the whole point here is now, if we know one of the functions in our composition is continuous, we just got to prove, which was this one, this is continuous. We just got to prove that the other function in our composition, is continuous. And Iman, what would I do here?
For x on the top, it's a straight line.
Okay, so for this, x, that's just a straight line. That is continuous, right? All right.
And for the second is also.
What do you mean the second one? Where?
In the bottom.
The bottom is called what? I almost told you. The denominator, which is x plus 1, that is also that's also a line, which is also continuous. So now, Iman, which one? This? No, that's this line. The diagonal just moves up 1. It crosses that 1. That's all. So, but they're both lines. So now, how can I say that this is continuous if both of these are continuous? What can I be like, okay, so my x and x plus 1 are continuous, but how does that make this continuous? Because the quotient property, continuity or whatever it is, right? So now this has to be continuous. And if both of our functions in our composition are continuous, that means our composition is continuous. That is good work. You guys seem to really get that. And we're going to kind of go further and further. And, I mean, it won't be easy. Trust me, calculus isn't easy. But the hard parts won't feel like completely lost. They'll be work, but it won't make you feel like you're completely lost, all right?